All right, how you doing, everyone?
Good.
Doing good? All right, so how was that exam from last week? Hard? Painful? Was it a surprise?
No.
I told you it was going to be total response. You got your input, you got your output, solve for your H of t. Then everyone remembered, like, I don't know, I'm just doing some y of t is going to equal to, I don't know, h of t convolved with x of t, correct? Right, and then you were supposed to solve for this guy right here. What is h of t? Right, and then it's going to be, I don't know, if it was analog, you're going to get, I don't know, let me just guess, c1 e to the, let me do a1 of t, correct? Plus c2 e a2 of t, correct? Right, does this look something familiar to your guys' exams, correct? Now I'm going to give you guys an answer. Hope you guys did this. Was that one of your answers right there? Did you guys put that on your exams? Everyone put that for every problem, 1 to 4? Because you're finding the impulse response. It's going to be a time. Or it's not this if it were h of n, right? It's going to be, I don't know, c1, a1 of n, right? Plus c2, a2 of n, or yeah, right there, right? U of n, right? Everyone got those answers? Not that hard of an exam? Or I don't know, it could be tough. And then basically your whatever input, right? If you have an input right here, if it's a delta function, right? What's the output? Just going to be your impulse. What happens if it's a unit step? Well, it's going to respond to it, correct? So you'll see your total response or whatever memory or input you put on there. Okay, that's good? All right, so let me go over what we can. So congratulations, everyone. By this time, or by this point of the semester, you guys have already mastered time domain analysis. You guys can do LTI systems and the time domain, right? Convolution. Was that fun? Painful? Yes, no, maybe, plus? Let's go. You guys did a lot of work. But then you're saying, well, there's got to be an easier way, correct? So I'm going to give you a general equation, f of t, correct? You're going to have some general function. All functions are going to be in terms of, I don't know, some amplitude, okay? And then it's going to be given some exponential, correct? And then some, I don't know, I'm going to call it alpha, or not alpha, yeah, alpha t, whatever. Just a general equation, right? And if you wanted more completeness, actually, no, I'll save that for later, okay? So you realize you can get this and transform this with a Laplace transform. Let me see if I can remember. Actually, let me tell you this. So remember how we had y of t, correct? And then some h of t, right? Some response, correct? And you're given some x. So you'll realize there's this thing called eigenvalues and eigenfunctions, to where, for example, if f of t, correct, was, I don't know, how do I want to say this? No, not f of t. X of t, correct, is like, I don't know, sine. It's just a sine t, correct? It's a wiggly sine wave, right? Right? And then you punch this through this magical box, correct? I'm going to call it h of s, or let's just call it lambda, or your eigenvalue, correct? Throw into this magic box, and your output is going to be something like, I don't know, let's just say it's going to have a phase change and some cool little thing like that. I'm just creating something weird. This is 0, and this is like I don't know, t delay, right? This is your y of t, correct? And what do you get at the output? I don't know, some sine wave, right? Sine t, correct? And then whatever the eigenvalue goes onto here, all right? And this eigenvalue is going to have some type of magnitude plus phase, okay? Is that good with everybody? If I put a sine wave in, I get a sine wave out, right? So this is constant. This is your magic number right here, all right? This is something that's going to come in your system. It's the same, okay? The thing that you're trying to figure out is this puppy, All right, and that's where we're going to start using the Laplace transform, okay? Is that good with everybody? All right, let me just go through some notes because let me see. Notes, and then you guys already went through all this. You guys understood you guys like this little example right here, right? RC filters. Do you guys know how, so let me just recall without going too crazy. Ooh, double, like that. Let me see if I can do this. If you wanted to solve for the impulse response of this, you know how you can just, I don't know if I'm gonna do this, you got this right here, and then let's see, how do I want to solve this for? You got some voltage right here, which is gonna be equal to, what is it? Some integral, I forget what it is, but, well, I do know this one. I of t is equal to c dv over dt. Is that good? Pretty simple stuff right there. And all you gotta do is, let me just show you. If this was x of t, right? That's your voltage, correct? You kick the box and you can get some type of h response from that. Is that good with everybody? So we can take this RC circuit and do the same thing what we did right here, all right? You solve for the impulse response. You just kick that box, you find out what it does. And based on what this does right here, I'll show you this. It's just that right there. H of t, 1 over RC, e to the simple RC time constants, all right? Is that good with everybody? Now let me show you what else I can show you. So you guys went through all this. Was it boring? Made you sleepy? What does this look like? You got your eigenvalue, you got your magnitude, right? You got your phase, correct? You just multiply this to your input and you're done. Is that good with everybody? Let's see, and then he went over this. And, oh yeah, let me show you this. So this is something I was trying to investigate too. And when I was going through this was, I want to do this problem. I want to prove this problem to me. So I have an example to show you guys. So let me see. Should I go through the step-by-step on how to program this, or should I just show you guys the answer? Answer, because we don't have enough time. Let's see. So let me show you this. So when you're doing analog convolution, you technically you can't really do like all the convs we've done convolutions have been in the discrete domain. So your time division was just 1 second, all right, or 1 unit, okay, 1 unit. The other thing to convert from a unit to whatever analog time, your dt, right? You're gonna have to scale this down, because if you don't, this convolution is gonna give you fat numbers, okay? So let's just copy this code by code, okay? Let me show you what it's trying to do, okay? I'm doing 1 millisecond. Is that good with everybody? You like that? Because I'm trying to, well, it's an analog signal, right? Here's our h of t, right? Oh, wait. By the way, does everyone understand what the unit step function is? Does everyone understand that when I do, hey, it's going to be 1 when it's greater than or equal to 0, correct? Is that clear with everybody? Easy answers. Here's our input, exponent, right? And then this is where I'm going to tell you why I hesitated on putting the unit step. Is there a unit step there? No. Why? Because we're doing bilateral Laplace transforms. Did he tell you guys that? No? Well, that's the hint of the day. It's all bilateral, but in the future, you guys are going to learn about the unilateral, and that's where you start putting your IC conditions, okay? So here's our H, right? Here's our X, right? X and H, right? Is that good with everybody? Now conv, all right? Convolution, all right? Is that good? So now let me just go through, okay. So you're going through his book, correct? And this is the answer he gives you, correct? So I want to calculate this. I want to know that I'm doing convolution correct? And then here's your answer, right? You like that answer? Does that look like a nice answer, right? So don't go crazy like how I did last night. Let me show you. So this is our real answer. That's that. So this right here was something I found in the actual, when you type in convolution, the length of y, what's the length of the convolution? It's going to be the initial lengths. It's using this, the length of x and the length of h as like some scale. So if x is like a 1/2 and h is like a 1/10, right? You're going to get 1 by, I think, 13 or something. It's going to get big. The signal is going to get big, okay? Because you're doing a shift convolution. So the way I did that was since I know the times are the same, they're all the same, I have to double it, okay? Is that good? I double the beginning signal and the end signal, and then I just know I have the 0 in the middle, okay? Is that good? Let me show you this. And then I'm going to set a force boundary, okay? I don't want to look through any other time. So let me show you this. My time here is from -10 to 10, correct? So the reason why you have to do a bigger time is that this signal is assuming infinity. You can't simulate infinity in MATLAB. You can only, like, what do you call it, do like, well, a finite number. But we're going to try and treat 10 as infinity. Is that good with everybody? If you go through the entire, I'll show you. No one wants to hear me talk. They just want to see it run. Let's show you this. Copy, paste. Guys like this? I'm doing MATLAB and lectures. Boom. Does that look good? That's your input? Okay, let me show you something else. You guys don't believe me. 2 seconds. Does that look like a e to the minus t, right? Pretty nice. And it's not a unit step. There's no unit step. It just goes to infinity when time goes negative, right? Is that clear? Now let me just punch in this puppy. X lim, well, it just forces the limit. Let me show you this. So if I do this, 10, right? Goes to, I don't know, 20,000. Is that good? That's a high number. But I'm going to truncate it by doing the following. You can truncate like this. Set your force limits. Boom. All right? So we're just chunking down the window, all right? So this is just to help you guys out with doing, like, proving yourself your homeworks or whatever. Or actually go through the whole book if you need to. So I know some of you guys are like, I don't want to read this book. This book's boring. Is that a good impulse response? That's our h of t. Does that look good? Our h of t is a finite number, right? It's got a unit step right there. See that unit step? Is that good with everybody? I'm going to convolve, okay? Let me show you this. I'm going to show you this, and I'll show you what I mean. Does that look cool? But now let me tell you this. What was our answer? 1/2 e to the minus t, right? So when t is equal to 0, right? What happens to this function? Turns to 1, right? 1 times 1/2 is 1/2, right? Where's our 1/2? I don't see it. This is where you need to start scaling and zooming in. So I'm going to show you what I mean. If you just zoom in like this, yeah, actually this is a bad example. I'll force it. All right. If you force your limits like this, does that look good? My output? Everyone understanding what I'm trying to do? Someone's not believing me. Let's check our answer, okay? This is the real answer, okay? This is what we calculated, right? This is our real answer. Is that good with everybody? Let's punch that puppy in. I'm going to punch this in right here. And then I won't set a limit. Does that look good? No, it doesn't look good because I got to put this limit. Are they the same? You like how you can do convolution now? So you guys can take this code, have fun with it, or I'll post it on the discussion thing. You can do whatever you want. But you got to understand that if you don't truncate it, you're actually doing a unique case where you have the following. Let me show you. Not that. Let me see. Is it this one right here? You can prove this here, but I'll tell you now, don't do it. You'll be sad. You'll be in pain. Don't do this. But this is just for that simple execution. Is that good with everybody? Any questions? No? Anyways, let's go through the whole notes. Let's see. Let me see what property. And you guys know how to do these region of convergences, right? You guys got to see the half planes and all these poles. Let me see. Man, I didn't even color it in. Can you see that? Okay, that's good. On my screen, it doesn't show it pretty good. And then you understand that the region, the ROC, region of convergence, can't have any poles, right? Because else the system blows up. Is that good? Let me show you what else. So is everyone clear with what we're doing? Let me see. Laplace transform, a two-sided function, region of convergence, finites, one-sided. Did you guys go over the one-sided unilateral stuff? Yes, what's up?
I have 2 questions.
Yes?
Do we have school tomorrow for Veterans Day?
So campus is not open tomorrow. It's going to be closed officially because it's a federal holiday. So no class tomorrow. So.
And then, how would you approach like Laplace? I know there's like different ways that people approach problems. Can you show us how you would?
Like a Laplace problem?
Like a bilateral transform, like a unilateral one.
Okay, yeah, I'll definitely want to go over that. So, but before I do that, because I want to definitely go over something. Let's see. You guys understand these properties? So I'll tell you this. You can go and prove all these, but we're not doing that. We're engineers. We need to make money. We need to make sure things work. Does everyone understand how these look like, right? You got your unit step, correct? 1 over s, and everyone's sleeping. Let's show you guys what's going on. If I were to show you another page, this is page 2. No, that's not page 2. That's page 3. Good. Page 4. I'm just going to show you how to practically use this Laplace transform. Let me see. Can I do this? It's not going to let me do it all. So everyone understands what a delta function is, right? It's just this speck of infinity, right, with time, correct? And if I wanted to put it into the Laplace transform, right, if I do a Laplace, correct, of S or whatever, is that good? So the Laplace domain, you're going to start realizing, how do I want to say this? From, if this was the real of S, right, and this is the imaginary of S, just think of the whole plane being raised up by 1 level of gain. It's hard to explain it, but let me just show you from the real value of S, correct? And this is just some value, okay? We're just looking at from a side view. So if I were to put my eyeball here, here's my eyeball, right? Is that good? And I'm looking through what this axis is, correct? Is that good? Scam calls. You're going to see that this level is just going to be 1 for the delta function. Is that good with everybody? And better yet, if I were to do this, let me show you a special eye. If I were to look like this, if my eye was like this, dot, looking this way, correct? If I were to do the following, let me show you a secret. Imaginary S, okay? Some value. It's also going to be 1, correct? But you'll realize later in the semester that there's a very special property with this, is that you'll get the Fourier transform from this. So what does this kind of look like if I have 1 of every frequency added together? It's just noise. You guys know what white noise is? White uniform noise. So like if I were to do like T of, I don't know, n is equal to noise. Is that good? Does everyone understand what I'm trying to do? Or better, do you guys know how the Laplace transform even works? Why am I even learning this? Want me to show you? Let me show you this. Maybe I'll show you guys a cool demonstration, but I'll show you this. Grab another piece of paper. Yeah, it's basically frequency responses. So if I were to do the following, let me see. I'm just going to do this. And this is my S domain, correct? This is real of S, correct? And this is imaginary. And let's just say our first point's going to be right here if I were to have a pole right here. Okay, this is pole 1, P1, all right? So I'll tell you guys this is going to be your favorite signal of all time. We have no frequency. This is going to be basically, how do I want to describe this? I'll just give you guys the answer. This is going to look like, if I were to draw, what do you call it? This is time, correct? It's just going to be DC. All right, is that good with everybody? It's just a DC signal. It's just a unit step. Is that good? I'm going to draw another picture, okay? Another one. This is P2, correct? And if I go up this, and if I were just to do the real plot, you're going to start seeing this sine wave, right? Is that good with everybody? And if I were to go up here, P3, it's going to be even a faster sine wave. Is that good with everybody? And then here, if I were to go down, let's just do P2 complex, correct? You're going to see something funny where you're going to get a negative speed or a negative frequency, but the only way to do negative frequency is just to go backwards. How do I want to show you that? It's just going to be the same as this. They're literally the same. These are called conjugate pairs. Conjugate pair. This right here and this right here. You see that right there? So if you need to have these two poles together to give you that cosine or your sine wave. Does that make sense with everybody? So this right here is going to equal, I don't know, e to the positive j omega or something like that, right? And this right here is going to be e to the minus j omega t. And you add that to get your cosine. Does that make sense with everybody? Is that good? So let's say if I do another pole over here. I'm just going to put a pole right there, all right? Just a nice pole. Pole, I don't know, pole R. And this is just going to look like, well, like this. Well, it starts at 1 and explodes. Is that good? And then if I go above here, if I put the pole over here, it's going to be a wiggle that explodes. Is that good with everybody? And then the same thing that's going to happen on this part too is you're going to have conjugate pairs, okay? When you have a pole that's imaginary, you need to have a complex pair. All right, so for example, if I were to do this following, let me just use another color, about purple or something. I think I already used purple. Is that good with everybody right there? Call this R2 or whatever, R2. All right, so what is this going to look like in the time domain? If we're starting at 1, right? It's going to wiggle down like this, all right? It's a transient. Same thing with this one right here. It's going to also wiggle down from 1. And you need these two poles because it's a conjugate pair, all right? Conjugate pairs exist together, all right? You got a positive frequency, positive imaginary, and you got a negative imaginary. All right, is that good with everybody? And then if I were to just stay on this axis right here, if the pole was right here, x, r, I don't know, 3, it's just going to be the decaying exponential like this. Is that good with everybody? How to use the Laplace transform, how you can get so much information from this? Any questions? But now you're saying, I can use the tool, but I want to pass my exam, okay? Well, I'll tell you guys that later, so let me see. Don't worry about this one. This is just a weird unit step function. These are the properties you need to memorize. Well, actually, just these two, if I were to tell you this. Let me see, what else do I want to show you? These are all just properties, and then, yeah, these two, definitely memorize them. These are very nice to memorize. Yeah, sorry for the quality, you guys. I don't have the notes. Now let me just check if I'm recording. Check. Cool.
David.
Yes.
What is Laplace actually transform? Simple words.
Laplace transform is just to analyze the frequencies of a system. That's literally what I just did right here. You just get
That's
wiggles.
the only thing being transformed, right? Nothing else you have to model.
So we're basically trying to figure out, Are you trying to say going from the time domain to the Laplace domain?
Yeah.
So that's if you just go from this signal, well, that's where I think I'll show you what I mean. That's where he was talking about these problems over here. For example, let me see if I can show you not the unilateral Laplace transform. Now I'll just show you guys. It's page 5, page 6. 6. So if you were given some, I don't know, f of t correct is equal to e to the minus t, right? U of t, is that good? And then you were supposed to find the Laplace transform, right? So if I were to give you, let's see, I think one of the things he was talking about is you can generalize this based on the frequency of this. So like if s is equal to -1, correct? You can get this by doing h of that -1, right? Of your x input, right? Is that good? So you're just going to get your eigenvalue. And for this one, let's just see where h of s is going to equal to minus infinity to positive infinity of h of t, h of t, yeah, h of t. Let me remember how he did it, because I'm not so sure what it is. Let's see, what did he say? He goes over it in his notes. I'm trying not to waste time on that one. Let me see. Where does he go over? He talks about it in like the first page. Literally this example, the same example I'm going over. You see that right there? And this is where I'm saying it's going to be very painful if I were, literally e to the minus st, correct? And you're going to have to do your convolution, right? But I don't want to do this convolution. It's going to be painful. It's already there, all right? So that's where you need to memorize this table, okay? Let me show you. So if you wanted to do your homework, here's your answer. See that right there? E to the minus t, u of t, correct? Where if I were to cross this out, a is equal to -1, is that good? Then what's the Laplace transform? F of s, right? Just look at your Laplace transform. It's going to be 1 minus s of a when a is equal to -1 is equal to 1 over s plus 1. Is that good? And then if you wanted to draw its Laplace transform, is real of s, imaginary of s, right? And then where's this pole? When do I get a pole?
-1.
When s is equal to -1, yeah? So that means it's going to be right here, right? -1.
Oh.
And then I'm going to draw my imaginary line, right? And that's my ROC. What does ROC stand for?
Regional convergence.
No, it stands for Republic of China. I'm playing. I'm playing, no. That's a joke that he would always say, but anyways, ROC, memorize it, okay? It's a right-sided function, and here's another property, and we'll go over this in the notes, let me show you an answer. Ooh, this one doesn't have my cap on. This right here is going to be, what do you call it, our imaginary axis. And I'll tell you practically, is the region of convergence needs to include this Fourier or this imaginary axis. Why? So it's stable. Okay? Is that good? So ROC needs imaginary axis, right? Memorize that, okay? So you know your thing's not going to blow up, all right? So let's say, for example, if I wanted to draw this, well, you already have the answer, right? Punch this into MATLAB. You guys want to see it in MATLAB? It's right here. Well, not really. Let me show you this for realsies. Here's my unit step, right? I'm going to put dot times u of 0. That's my unit step, right? Exponential e to the minus t, correct, right? There it is. We just drew that. Okay? So if I wanted to translate this plot to real life, it's this right here. This is, you can get the inverse Laplace transform going from here to here in Laplace transform. All right? And how do you describe the system? All right? It's stable, right? And it's causal, based on the ROC. Does that make sense? And does this blow up right here?
Why is it causal based off the ROC?
Huh? Because it's a right-sided function. Right-sided. Right? Because we're going to the right. So if it's going to the right, we're going... What's the definition of causal? If it goes from t is greater than or equal to 0, right? We're not going negative. So it's a real function. We're going from real time to the future, right? It's just our system running.
So if it's non-causal, then it's left-sided?
So yes, if it's non-causal, I'll show you guys some examples. That one doesn't have a cap. It's page 6, page 7. Man, you guys are getting your money's worth, huh? So let's just say it's e to the t, right? Right? What is this gonna look like? It's gonna blow up, correct? It's gonna go from like this, right? Just gonna go to infinity, correct? Is that good? But let me tell you this. Let me see. Does he actually give you e to the minus? Let's see. He doesn't give it to you. Because I'll tell you, this is going to blow up for sure. And the only way to make sure this doesn't blow up is if you put u of minus t. Okay? Is that good? So now it doesn't go like this. Don't think like this. It actually just does this. And then it just stops there. Okay? For time. All right? It's stable, but it's non-causal, right? Chapter 2 or chapter 1, signals and systems. Is that good? Because our function just exists, but it's negative time. Does that make sense? However, the pole for this one, and I'll just cheat the answer. Let me see, actually, e to the t, u of t, minus e to the t. So technically, let me see. If you wanted to get this, you need to have a minus sign here, but let me see. I'm wondering, because we need this condition to happen. There's a negative here. I'll tell you that, but that means this has got to be flipped, which I don't like that. Yeah, let's just do Laplace transform of x of t is going to equal to minus 1 over s over a. Is that good with everybody?
Yes.
But 1 second, you said negative time in terms of the non-causal?
Yeah.
What do you mean by negative time?
So if I go from t is less than 0, that's what I mean by like negative time. Does that make sense? We're in all the non-negative or the negatives time.
As you turn the machine on?
Well, what do you mean? So when I'm saying negative time, I mean everything that's like to minus infinity time. We're just going this way, all right? So it's something stored in our memory. I don't know.
Oh.
Does that make sense? It's not a real system. It's already started, but we just have these numbers.
Okay. Like the presets.
Kind of. Yeah, I see what you're talking about. But for the Laplace transforms, especially for control systems, we're dealing with stable causal systems because we want to turn them on. We just want to see these things turn on in real life. But back to this, the pole for this one is going to be at, well, when s is equal to, what is our a? A is equal to, what do you call it? 1. That means this is going to be equal to minus s minus 1, right? Is that good? So that means our pole is going to be at 1, right? So that means our pole is going to be right here, correct? So let me see. If I were to draw our imaginary line, correct? Technically for this example, because I do have this, what do you call it, stable system, correct? It's, or not, it's a stable, but it's non-causal, correct? My region of convergence is going to be this part right here. Does that make sense? It's stable, but non-causal. Is this clicking with everybody? I need, the ROC needs to include this imaginary axis, and it's stable. It doesn't blow up.
Do you mean like it's centered at the origin?
Centered?
If it's if the ROC is stable, it needs to have the origin as a.
Yes, it needs to include this entire not origin, but this center axis, the imaginary axis, because this is how you are able to do your Fourier transforms. Or do you want me to show you even a practical thing? So if I were to do the following and draw our eyeball going, I don't know. Or let me just choose this orange color. If our eyeball is going this way, correct? And if I were to draw, I'm going to draw some really practical thing. J omega, correct? This pole is going to dominate on this axis, correct? But technically, it's going to be on the other side. It's going to look something like this, where this is going to look like some filter. Filter. And this is like some magnitude, 20 log dB. Does that make sense? So you can technically create like Bode plots and all these other like transform, or what do you call it, like Bode plots, frequency responses, based on this. But this is a bad example because technically the pole should be on the other side because we want to have a stable causal system because we're turning on our function generator. But this is kind of what it's going to look like. This pole is going to dominate this, all right?
So we would shift the pole to the 0, 0, or I guess just to the 0, x.
The pole? We're not shifting the pole. The pole just exists there. It's at 1. The pole is at s is equal to 1. But for the region of convergence, we need to include this because that's what the problem is looking like.
So would we then, if we're adding a filter, the filter would look like the graph starts after the...
Yeah, kind of. Oh, actually, here's the other thing. There's a minus sign here, so technically this should be flipped because we have negative values, so it should be the other way around. Does that make sense? Or actually, no, because since it's magnitude, it's not. But does that make sense in a way? Yeah, someone wants me to do the MATLAB, right? Just show you a better example. But anyways, those are the properties. I recommend you memorizing some of them, especially this guy. These two right here are going to be on the exam, okay? All right, he's going to put a non-causal system on there. All right, so you got to understand the region of convergence and how to draw your actual signals. Okay? Bilateral Laplace transform. Let's see, linearity property. It just tells you can add things together, okay? A of f of s, two systems, okay? Let me see. Should I go over all these notes or should I just go over the thing that matter? Things that matter, okay. A function that is not Laplace transformable. Does everyone understand that this 2 to the t, u of t, explodes, right? And this one also explodes the other way. So it's not a Laplace transform. You can't roll. Let me see. -2. I know what it's doing. Let me draw this one for you. Page 8. So let's just say you have this thing where the poles are given to you as, here's your Laplace transform, L of s is equal to 1 over s plus 2 plus 1 over s minus 2. But he gives you the condition that, what's his name? R of s has to be less than or equal to minus 2, right? And this one is R of s is got to be greater than or equal to 2, right? So this is going to only exist from like -2 to -infinity, correct? I'm going to draw this pole right there, okay?
Yes.
And this one's going to only exist from +2 to infinity, right? So what does that ROC look like? Boom, 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 boom. So it's going to exist like this. This is a problem that you're forced, okay? Boom, 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 boom. So tell me this. Is it stable?
Yes.
Why?
Because it's centered with the.
Does the ROC include the imaginary axis?
Yes.
Yes.
No. Right? This is the imaginary axis, correct? Here's my ROC, right? ROC1, right? ROC2, right? Let me just make this bigger. Does my ROC, any of these regions of convergence include the imaginary axis? No. So that means it blows up, right? This system, if you try to run this, it's going to blow up. All right? Now tell me this is a causal.
Causal if it's right-sided, non-causal left-sided.
There you go. This right here is a causal, right? This ROC2, this belongs to this guy right here, all right? And this right here is non-causal, right? Because it belongs to that guy right there, okay? So this is causal, right? But unstable, right? And this is also unstable. Does that make sense? When he throws this on the exam, you're going to say it's unstable and you know how to do the Laplace transforms?
What would you add to make it stable?
Well, you can't really do anything other than this is the problem he forces onto you.
If you add like an I somewhere, does it make it stable?
Tell me this. I give you a capacitor, right? And it's charging, correct? It's charging to infinity, right? Here's my battery, right? I'm charging it and it's going 2t. Can you draw that picture for me? How do you fix that capacitor? You can't. It's because the only way to fix it is just to turn off the U of t.
Make it an imaginary U of t?
Not really. Unless you go backwards. Unless this time gets negative, you can flip it to the point where I wouldn't try it. Don't do it. The point is, do you understand what this system looks like just by looking at it? I'm trying to train you guys. Look at this system. Does it blow up? Yes or no? And if you know it blows up, then can you draw the ROC in real life?
Yeah.
Is that good?
If you're looking at the E give you something general, and then I guess what do they call it? The -1 in front of the E, and then the -1 in front of the 2t.
Yeah, so if you go to -infinity, right, time, well, this doesn't exist, but this does. This unit step turns on, and then negative and negative turn to positive, so you have 2 times infinity. T, e to the infinity, it's also going to infinity. Does that make sense?
Yes.
All good? And basically, you can do this. Here's region that converges 1, 2, boom, you can solve your exam. Boom. Easy. Laplace transform of a finite duration signal function. And can you guys do that? Yeah, you guys should be fine. Signal reversing. This is what I was talking about. If you wanted to reverse your actual thing, let's see. Does he do that for you? Let me see. Laplace transform, you have some function, you're reversing it. Boom, minus S of t. I think I want to see if he does this. Okay. I think this is it. I think this is it right here. Okay. Maybe, right? Region of convergence is less than minus a. I don't like that. S is not equal to that. Minus of a. It's okay. Anyways, Laplace transform or time reverse signal. This one, if you make the n go to it, well, this is, what is this? Why does he have n in there? Oh, a power. So like, I don't know, n is equal to 2, correct? It's a square. So if you go to it, well, infinity time, let me just see. Region of convergence, signal reversing property. Is everyone understanding what's going on with these things? It's just a bunch of properties you gotta know. So I'm telling you this. Lasham's outline book goes over this. So I'm just trying to run through everything I can. Let me see. Laplace transform of a reverse two-sided signal. Oh, is this it? Reverse two-sided signal. I'm trying to figure this. You guys remember this one? But it's a different way of approaching it. Remember that when you go to infinity, it blows up, right? But I don't think this is what it is. You're just solving problems. That's all it is. All right. So that's literally all I can say about all this. Signal shifting. You get some type of like shift in the phase. Is that good with everybody? Signal shifting property of the Laplace transform, man. These are all notes. What else did he assign you to guys watch? Just properties and everything? Is that good? Yeah, I'm trying to figure out what you guys need to learn. Let's see. Laplace transform of a shifted Dirac delta. You know this right here. This is literally just e to the st naught, just a shifted pole. Or not shifted pole, it's just a phase. That's it. Laplace transform of a time shifted shift. No, I don't want to read through all this. Time scaling. You can read through this in the Sham's outline. That's all I'm saying. That's all you can do. Let me see. A of t, f of s. Let me see. Boom. Let me see. Laplace transform of a time-scaled signal. Man, you guys got a lot of things going on. I'm going to go to the real stuff. Let's see. Laplace transform. Conjugates. Real signal property of a Laplace. Let's see. What else do I have? Imaginary signal properties. Let's see. Signal property. Convolution. No, I don't like these. I want to get to the fun part. Oh, is this it? Is this it? Is this it? Ooh. Yeah, this is it right here. So here's another part you got to memorize. And this is where the goody parts come into play, and I want to show you this. Page 9. Let me show you this. Boom. So there's going to be a thing where, why are you going to have the point where, let's just say, we have the function where it's like d of, I don't know, d of y of t, correct? Over dt, right? And plus, I don't know, y of t is equal to, I don't know, x of t, right? And then you got to put this all through a Laplace transform, or a Laplace of f of t, right? So this right here is a good problem right here. Memorize it. You're going to learn it. Love it. This is going to be on the exam as well. That's why I'm trying to speed through this. Where basically, if I have, let's just do Laplace transform of d of n, f of t, right? dt of n, correct? It's going to equal s of n, f of s, all right? So what does this mean? So for this dy of t, right? It's 1 and 1, right? What's this Laplace transform? Based on this, it's going to be s1 y of s, right? Is that good? And then this y of t, what's the Laplace transform of y of t? Y of s. Is that good? What's the Laplace transform of x of t? X of s. Simple. Yeah, this is going to be a tool that will be useful for later on when we talk about the unilateral Laplace transforms, okay? This is one you got to memorize. And then, so if it's d2 of y of t, right? If there's a second, a second derivative, right? So let me just write another marker. If you're given like d2 y of t, right, over d2, this right here, it's going to convert to s2 of, y of s, okay? Is that good? Does everyone want to memorize this on the exam? All right? I'm just giving you guys some hints. Let's see what else I got, because I don't like, these are all making me sleep. Let's see. And then he goes through an example. So if someone's saying, hey, David, I don't believe you Well, here's the textbook. It tells you, if you don't believe me, we're going to prove this, and he proves it like this. Does his infinite integral, boom. He solves for it, and then let's just see. You guys know what QED stands for? You went over it in class, right? Yeah, quad something, I don't know. I don't know. Like, proved, I don't know. What does QED stands for? QED meaning Latin. Quod erat demonstratum, which means, yeah, just it's proved it. I just demonstrated. That's literally what he's saying. He says, if you don't believe me, here's the proof. Is that good? Anyways, let's see what else he does. Proof by induction. What the heck? Oh, so he says, okay, I'm going to just put a -1 and just scare you guys. So this equals this. Oh, okay. Okay, S, L, and what the haze did he do here? Man, this is why he's Dr. Stuberud. He proves it a second way. There you go. So he says, I don't want to prove it n times. Like, okay, I'm going to prove the second order, third order, up to the nth order. He just says, if I just show you, well, n-1, and then look at the differences between the current case and the previous case, I can get all cases, S of n. All right, that's his proof, okay? So memorize that, all right? That's going to be on your exam. I'll tell you that. Let's see. Terminal Laplace transform with a delta function. Ooh, wasn't this one on your chapter 2 signals systems? Yeah, I don't like this. Let's see. Laplace transform of the derivative of this. Ew. Looks nasty. Signal partial differentiation property. Because I don't want to go all over all this, and because it's just a bunch of work. You guys can read the notes for the proofs. Signal integration, signal property. You guys don't need to know that. Laplace transform differentiation. What tarnation is this? Let's see. Because I want to go over some cool stuff. Integration property. Whoa. Yeah, there's a lot of notes, y'all. Let's see. Laplace transform of this. No, I don't like these notes. Summary of the bilateral Laplace transform. And he just reproofs everything. Here's all the proofs you need to memorize. Well, not memorize. I would just say linearity, because everything is linear time invariant systems. Signal reversal, not that bad. You just change this S. Signal shifting, time scaling. This one, definitely memorize this one. Very important. And I think that's about it. This one's just funny. I don't like that one. It's just basically saying if you have a function like, I don't know, sine, right? A cosine, and you're multiplying that by like time itself. So it's just interesting. And then I'll tell you this. I don't have the actual like finished notes of the he didn't give this to me, so this is where how do I want to explain this without cheesing it? Let me see if I have another folder. Unilateral. Do you guys have the full unilateral notes? No? I thought I gave you guys that last week, Wednesday. Packet 2? Yeah. Was it signal differentiation property? Let's see. Okay, this is important, y'all. So, let's see. This is another, so remember this part right here, this first half right here, the derivative of some time, right? Some function d of yt, right? Derivative of y of t, right? Gives you s, f of, or y of s, correct? Well, there's a thing called an initial condition that just pops up. And if you want to see that proof, let's see, does he prove that right here? Yeah, he does prove it right here. He says, let's go from this to this, boom, boom. Gives you the negative or initial condition. Ooh. So yeah, this is another thing I would memorize, okay? I want to go over a problem. Let's see, what else do I have here? No. Unilateral Laplace transform? No. Oh, okay. I think I want to go over this one right here because this one threw me off when I was an undergrad. So let's say you do have a second order equation. Let me show you this. D squared y of t, correct? dt squared, right? I want to solve for the Laplace transform of this one right here. So here's your little equation, but I want to force this into your guys' brains. It says the Laplace transform of d of n of, I don't know, y of t is equal to this right here. Can be simply given by s of n, f of s, right, or y of s, right, minus this sigma right here, sigma summation, right, n minus 1 from m is equal to 0, s of n minus 1 minus m, d of m, f of t? No, y of t, dt of m, where t is equal to 0 minus. That's an ugly equation, okay? But we're going to punch in numbers. So what's the first part going to be when n is equal to, 2, right? And what's our m? Oh, okay. If we have this n equal 2 condition, right? We're going to plug and chug this n is second order equation, correct? Into this, right? So I'm going to get S2, right? Y of S, right? Remember this part? The thing I'm forcing you guys to memorize, right? This is going to be on the exam 5, okay? Minus, right? Now we have all this funny business right here. 2 minus 1 gives you 1, right? M is equal to 0, right? Of S, 2 minus 1 minus 0. D of, let's just do M. This is going to be a lot. Does that look good? So this is actually going to be 1 minus M. Is that good with everybody? Let's just brute force this, okay? So for our first number, when M is equal to 0, right, we're just going to get, S. And then this right here, since it's 0, D0, what is that? How do I show you guys this without making it too difficult? S. What is this? Maybe we'll have to ask Dr. Stuber about this right here. Then minus, when that's equal to S0 right here, D of 1. I'm wondering if this is what it is. D of 1 dt of 1 y of t. Because this is going to turn into something beautiful that I need to show you guys. This is page 10. Yeah, this right here is an ugly one, but let me show you there's a cheat way. You see. That's all nasty math. That's all nasty math. Let me see. There's no proof. I don't like this. Let me just go over it to you. The thing you need to memorize for the exam. So if you have the following, d2 of yt, right? dt, like that, right? Your first term is going to be this. You're going to memorize this, okay? Right? Minus, let's see. It's going to be s. And I'm trying to remember if this is what it's going to be. S of... let me just see what he's got. I feel like I have an answer here. Laplace, not LTI Laplace. Inverse Laplace. Let me show you this. Where does he go over it? Laplace transforms. Stable system. non-causal, causal. Let me see. Doesn't give it to you. Where is it? Because let me show you this, because basically what I'm trying to do is just change this ugly equation into something nicer. And I can't find it. Let me just see. Unilateral Laplace transform, second order. There we go. Is that good? Where is that proof? That's what I'm trying to find right here. Where are you, little guy? No, that's not what I want. Where is my unilateral? Unilateral Laplace transform. Let's see. Yeah, it's this puppy right here. See this right here? Yeah, okay, so I was kind of on track. So S of, okay, let me add you this. That's what I want you guys memorizing. There you go, that's your initial condition. And then minus, what do you call it? Y prime of 0. Yeah, there you go. That's what you memorize. All right. So your initial condition when like some voltage, right? 1 volt, correct? And then some derivative, right? I don't know what the change is, if it's an inductor or a capacitor, okay? So this is what you're gonna memorize for your exam, all right? Is that good? And then same thing where if it's d of y of t, right? Over dt, correct? You're going to have the following. Remember this, y of s, just one order, correct? This is the easy part. Minus y of 0. Now, okay, this is looking familiar. Is that good? And then regular y of t, right? It's just going to be y of s. Add those up, solve for your given initial conditions. Is that good with everybody? Any questions about that? Let's see, what else do I have for you? Because I could go over inverse Laplace transforms, but I'm not so sure. Let me see. You guys want me to talk about your assignment? So, busy editing it a little bit. Laplace transforms. Let's see if I can show you this. Z-plane. Let's see if I can show you something. Because I want to show you this. Let me see. Laplace transform. Who wants me to do this? Let's see. I don't want to do that. Because I think what I want to try and show you guys is this. Not Z-plane. Pauli, this, gains, residue. Yeah, let me show you this. I don't want to copy that one. Determine the system transfer function. Let me see. But yeah, that's all. That's what I'm trying to show you guys right there. But let me see. Is this packet making sense? It's just Laplace transforms, and you're trying to go from some function time into some, what do you call it, S domain. Is that good? And then for the next class, I'm going to go over inverse Laplace transforms, but this one's flipped. Let me show you this. X, change editor. There you go. Run this here. Yeah. Inverse Laplace. And then let's see. Organize, rotate 90 degrees clockwise. All. Yay, there you go. Inverse Laplace transforms, but I'll go over that next class, okay? But let me see if I can show you guys one thing. I want to show you guys some more MATLAB. Let's see. If I go to plot 4, let's see. MATLAB, boom. Boom, MATLAB. So I think what I wanted to show you guys is this right here. So you see this right here, this transfer function right here. If I were to do the following code right here, right? Figure 1, It's going to be this. X, boom. Oh, that's not right. There you go. Does that look good? Can you see that right there? Okay. You see what I'm trying to do right there? Just drawing poles and zeros. All right. Let me see. I want to show you guys something. If I wanted to show you poly roots, let me show you this. Now let me show you this guy right here. What does this guy do here? Okay, 1, 3, RPK residue. X residue do. And figure 1, plot H. It's not right. Let's see. Ooh, look at that. T, H. Ah, you see how you guys are going to do your assignments now? So I'll be posting this later. And well, first I got to ask Dr. Stuber when your guys' next exam. I really don't know when this exam's going to be. So he'll let me know by, I think, Wednesday, so I can figure out what I'm supposed to show you guys, all right? But the first thing I'm trying to make you guys memorize is just this. This is what you guys are going to see in your Shams outline books, okay? This right here is really important right here. Given initial conditions, this is what you're going to memorize, all right? Answer 1, this is probably going to be 2 questions on the exam. And then the other question is going to be, what do you call it? Well, drawing regions of convergence, right? Understand how to do that. And you can start realizing Laplace transforms, well, yeah, it's a lot of work for the, integrations. But once you understand it, it's a really easy tool. That's why I say there's not much to go crazy other than knowing the properties, knowing how to do it, how to do the actual integration. This is where it's your guys' job to do the written homework. And I'll demonstrate that right now. I'll show you guys. ComSys. There you go. Boom. E25. Where do you give you your computer homework? This one right here? No, not that one. 25. Signal systems Laplace. Wait, where's your guys' homework? Homework? Oh, thank you. Chapter 5. Is that good with everybody? So let me give you guys a big tip, and I don't know if anyone's caught it. Has anyone realized how Dr. Stuber is actually doing his attendance? Your attendance, let me show you guys, because you guys need to know this, and that's big help. Yes, Dr. Stuber is hearing me because he knows. 2% of your grade, right? This is considered your attendance. Did you actually put effort into this class? 2%. That's how he grades you too. So practice the homework. That's how I know you guys are paying attention. It's a lot of homework, I know, but there's no other way to show you other than practicing the homework. So if you do the following, that's how he keeps attendance. So 6 classes, 6 exams, turn in your written homeworks. And if you realize the Shams outline textbook, for those who don't know, ding, ding, ding. Let's see if I were to go over a problem. Chapter 3, let's look at chapter 3. Laplace transforms. This book also does a really good job at explaining everything. 22, 27. Let's go to 30, problem series. Let me see. 37. See how it shows you, you're given some equation right here. I don't know if you guys can see that there. I don't want to show you that. Derivative of y at t plus a of y at t, right? You're given some equation, and you got to go over, what do you call it? Let me see. It's not going to let me do. It goes over the solution, okay? And based off this Shams outline, that's where he starts picking at your home or your exams, okay? And then you see, look, here's your end answer, which is going to be some function of time. Well, this one doesn't have a unit step, but he'll give it to you. Solve the second order linear equation. Second order equation. And boom, there's your answer right there. This probably is going to be a problem he's going to pick. Actually, this is a nice number. 1, 5, and 6 as a poly, right? That's your terms. You find the roots. Pretty much simple. Is that good with everybody? Next class, I'll be showing you guys how to use the Heaviside function so you guys can get your inverse Laplace transforms. Is that good with everybody? All right. Have a good day, everyone.